The method of integration by parts. This is another method that is very useful for us to calculate the integrals. Suppose u and v are differentiable functions. Then the integral of u dv can be written as uv minus integral v du. The choice of u and dv is a little bit tricky. By practice, we feel more comfortable about choosing a correct u and a correct dv. Some popular examples are as follow. For example, if you're asked to calculate the integral of x e to power x, what's the approach in calculating this integral? Substitution doesn't work here. We're going to apply the method of integration by parts instead. So let us take u to be x. Then du is equal to dx. So taking the derivative of u makes it much more simpler. Now take dv to be e to power x dx, which is this quantity just right here. And then if I want to calculate v itself, note that in the formula you have uv. Down here inside the integral, you have a v. So we need to drive v. How do you get rid of dv? By taking the integral of both sides. The integral of dv is equal to v. It must be equal to the integral on the right-hand side. So v is nothing but e to dx. Well, we have all the missing pieces. We just need to follow the integration by parts formula and calculate the integral on the right-hand side. So this integral is uv, which is x e to the x, minus the integral of v du. And v is e to the x dx. Please note that this is a familiar integral. We simplified our original integral into something much more simpler. This is the goal. That's why I told you at the beginning, the choice of u and dv, we need to practice. For example, here, if you took u to be e to the x and dv to be x dx, then v becomes a quadratic term, which makes the integration a little bit more complicated. So as long as you see a familiar integral like this, it means that we are happy. We can continue. This integral is x e to the x minus the integral of e to the x dx we all know is e to the x. Don't forget the constant of integration. So by the method of integration by parts, we are able to solve this integral. The integral of x e to the x dx is x e to the x minus e to the x plus c. You can take the derivative of the quantity that you just found and show that it is indeed x e to the x. You can always check your work. So if I take the derivative of x e to the x minus e to the x plus c, this becomes d dx of the multiplication between x and e to the x minus the derivative of e to the x, and the derivative of c is just 0. So applying multiplication rule, you have the derivative of x, which is 1, times e to the x plus x e to the x minus the derivative of e to the x is e to the x. So as you can see, these two get canceled out and you're left with x e to the x, which is the same as the quantity that you have inside your integral. So we checked our work. It means that our calculations are correct. But again, please pay attention. If you decide to take u to be e to the x and dv to be x dx, du becomes e to the x dx, and v is the integral of x dx, which is a half x squared. So if I follow this formula, now I have uv, which is a half x squared e to the x minus integral of v du. I have a half x squared e to the x dx, which makes it more complicated. Now I created a quadratic term inside the integral. So this u and dv doesn't work well. U is equal to x and dv is e to the x dx. That gives us a nicer method to calculate this integral using integration by parts. Consider the following. The integral of x sine x. The previous one was x e to the x. So we took u to be x. Well, let's see. If I take u equals to x, then du is equal to dx. Okay. If I take dv to be sine x dx, then the integral is easy to calculate. dv, which is sine x dx, to calculate v, we're going to take the integral of both sides. You have v to be negative cosine x. Very well. So let me plug in everything into the integration by parts formula. The integral of x sine x dx is uv, which is x times negative cosine x, minus the integral of v du, which is negative cosine x dx, which is super easy to calculate. So we don't have any issue calculating this integral. It means that the choice of u and dv were correct. This integral is negative x cosine x, and the integral of cosine x is sine x. Don't forget the constant of integration at the end. And that's how we calculate the integral using integration by parts method, which is very popular, very easy to work with. And I highly encourage you to practice as much as you can to feel comfortable about this technique. Another popular question is calculating the integral of ln of x dx. Well, in order to calculate this integral, we're going to apply the method of integration by parts. So what's the very first step? Let us take u to be ln of x. du, as you know, is 1 over x dx. So what is dv? dv in this case is nothing but dx itself. So if you calculate v, v is equal to x. Now that we have all the missing information, we can follow the formula. The integral of ln of x dx is uv, which is x times ln of x, minus the integral of v du. V is x, and du is dx divided by x. But these two get canceled out. You're left with the x ln of x minus the integral of dx, which in turn is equal to x ln of x minus linear term x plus constant of integration. So this is the method of integration by parts, helping us to calculate some of the integrals that are usually difficult to calculate. Some students make this mistake. They say, hey, we can use u sub here. If you try to use u sub and take u to be ln of x, then du becomes 1 over x dx, and then they say, hey, dx is equal to x du. This is one of the warnings that I told you, that when you're using u sub, you need to make sure that x is actually there. But when you're taking a look at this integral ln of x dx, there is no x involved. So u sub doesn't work. You cannot just create x inside the integral by doing the substitution this way. So it's not working. We have to use a different method, which in this case is integration by parts.